All right. Good morning, everybody. Let's start about how to analyze function families. And, we're going to be looking at, as you can see here on the worksheet, we've got a function, we've got a graph, and then it says parent function, D, R, number of roots, in behavior, increasing interval, decreasing interval. Our main job today is to look at a function, look at a graph, and not only know how the picture looks, but also to describe the picture. You can't always just describe a picture by saying, hey, it looks like a V, or, hey, it's upside down. Sometimes you need to qualify or quantify very specific things, and that's why we'll get into all this stuff. Some things that you might want to keep in mind, okay? Last week, we did a very brief sketch where we had 8 of these things, and we learned about some different graphs. A line, a U, a V, a wave type thing, a swerve type thing, an S type thing. We learned about all 6 of these different graphs. We didn't get here yet. I guess that makes it look like they're X's. We didn't get there yet. We'll get there next week. Maybe on Wednesday, Thursday, but we learned about these 6, and then we also learned about the transformations. And I used a car, and if you didn't see it, you're probably going to think I'm crazy here, but we learned about how you have X plus H plus K, possibly a negative sign out front, possibly an A out front, and the H moves you left or right opposite. The K moves you up or down, and it's not opposite. So if you want to write same here, I guess, but you don't need to. The negative sign does a flip where it will flip you upside down, and the A does a stretch or compress. Now, again, this is all notes from last week. This is how we're going to be moving our families around. And so we also talked about Desmos and how to get Desmos to do these graphs for you. So what we're going to do is when I go through the notes today, I'm going to be trying to do it all kind of from my head, but I will always end up saying, if this doesn't make any sense, just type it in Desmos. And so when we're looking at this first one, we've got a linear graph. Now, one thing that I would say is let's go ahead and list our transformations here. This doesn't necessarily say that we need to do this, but it's really good practice. Okay, now linear graphs, it's not that relevant, okay? But we do have a linear graph. Linear graphs are kind of weird because they're not really in vertex form, technically, because linear lines are just lines. They don't have vertexes. But we know, for example, that the slope is -3, that the y-intercept is +5. Okay, this is just a linear, regular old line, Algebra 1. That's supposed to be a 3. And so let's go ahead and graph that. Go up to +5, 1, 2, 3, 4, 5. Slope of -3. Remember, slope is rise over run. We're going to be rising -3, running 1. Go down 3, run 1. Go down 3, run 1. Go down 3, run 1. And then draw our line. I was really bad at straight lines before, so let's see how this looks. There we go. It's not great, but it's getting there. Let me make sure I don't go. Okay, so there's our linear line, okay? Now, some of the stuff over here is how we're going to need to describe that stuff. And some of this stuff you've heard of before, okay? So, for example, parent functions is something that we talked about last week. This is something that you should have heard of before. A parent function basically means all you get is a y and an x, and you need it to make the very simplest form of the line, okay? And so if we look over here, the slope of -3, we're going to have to lose that. The 5, we're going to have to lose that. We're basically going to lose all the numbers, okay? And so a parent function, especially for a linear graph, is really easy. It's just y = x, okay? The parent function is the simplest, most basic, original function that you get. We've also heard of roots before, It might have been a while. Well, it definitely was a bit of a while. And we talked about 4 things that were all the same. Okay? You could have roots, which was the same thing as x-intercepts, which was the same thing as solutions, which was the same thing as zeros. And those 4 things are all the same. Okay, and so looking at this graph here, number of roots, I would probably think about this, maybe do one of these little swaps and say roots is the same thing as x-intercepts. So this is really asking us about x-intercepts. We've got one of them right here. So I'm just going to go ahead and put a 1 there. So again, that should be relatively easy. You probably might have forgotten that little table of all the things that are the same, but that's okay. Now the rest of this stuff, end behavior, increasing, decreasing interval, definitely a little bit new. But domain and range is also something that you've heard of before, right? You've at least heard it mentioned before. I remember hearing it in like 4th grade before we were even looking at graphs, and we were looking at tables, and we were looking at, you know, how many M&Ms did we have in the bowl and stuff. I remember all these weird questions. So domain and range, very simply, you need to know this, that domain has to do with x and range has to do with y. If you're not confident with that, write it down every single time. My biggest way to remember which one is which is you'll always see domain listed before range. It will always be domain and range, and you'll always see x before y. And so you put the first ones together, you put the second ones together, right? Domain and range, x and y. Domain is x, range is y. That's the easiest way for me to remember it. And what these questions are asking is, I'm going to go up here and maybe write something. Okay. Domain. You don't necessarily have room for this on the papers that I've passed out to you, but if you want to maybe add this to the back of one of the study guides or something, domain is where is your graph. Okay, that's what it's asking. Okay, now, not only is it asking where is your graph, it's asking where is your graph in terms of x. So maybe we don't need this parentheses or this question mark that's halfway through. Specifically, what values of x could you find your graph at? And so here's the easiest way in my mind to think about domain. Okay. Pick an x value. Let's pick this x value right here. Okay. Is my graph anywhere at this x value? Yes, right? My graph's right here. And so my domain, well, 3, right? Right there at 3, there's my graph. Is my graph at 4? Yeah, it's down a bit further, but my graph's somewhere at 4. Is my graph somewhere at 1? Yep, it's right here. Is my graph somewhere at 0? Yep, it's right here. Is my graph somewhere over here at 6? Well, it doesn't look like it, but I'm sure you guys are smart kids, right? I mean, the graph is going to keep going. It's going to be here-ish. And is my graph at 6? Yes. So we talked about 1, 3, 4, 5, 6, 0. I'm sure you're thinking to yourself, this is ridiculous. I'm not going to write down every single number where my graph is. Okay. Is my graph out here at -4? Yeah, it would be up here, but it's there, right? So is my graph over here? Yes. Is it over here? Yes. Here? Yes. Is it in the middle? Yes. Is it on the end? Yes. Is my graph everywhere? Yes. Okay. Now, who cares about how high it's going? Can we find it here? Yes. Can we find it here? Yes. Can we find it here? Yes. And so the domain is everywhere. It's every single x. Okay. Now, what we're going to be able to do here is we're able to write this a few different ways. One way that we could write it is what is the smallest number where our graph is? And the answer would be negative infinity. And what is the highest number where our graph is? Positive infinity. Again, I'm sure it's clear to you guys that this graph is headed this direction forever, and our graph is headed this direction forever. And so our graph is literally everywhere. So that is a totally legitimate way to write our domain. Remember, we're always going to use parentheses with infinity signs because you can't quite include infinity signs. Now, there's a better way to write domain, to write this negative infinity to positive infinity. Because what we really mean is everywhere. And this is a lot of stuff for us to write if all we mean is everywhere. Okay? Mathematicians are very lazy, and they come up with shortcuts for everything. Some shortcuts, we've got backwards E, we've got upside down A's, we got these things, we got all different kinds of weird symbols. Okay, now, they all mean different things. You'll learn about them in higher levels of math. But the one we're going to talk about today is one that's called all real numbers. And you may have seen this symbol before, but all real numbers, you're going to write two lines, kind of like the number 11, two lines back to back, and then you're going to draw the R curve on top of that. It's basically a fancy R. It's basically a capital R with two lines in it. Some people like to draw the R first and then the two lines. Some people like to draw the R and then give it an extra back on it. I like to do two lines, draw the R. It looks pretty good. Okay. Now, what this means is everywhere. It means every single real number. Okay. And so for the most part, this is not very common. This is going to be super common. Okay, and this is something that is not just something that I'm making up. This is something that would be on the SOL test. This is something that, every teacher has seen before, all real numbers. Okay, so now let's talk about range. Your range is very similar to your domain. I guess let's go up here and talk about it. It's the same exact thing, except for you're talking about y's now, right? So where is your graph in terms of y? So it's the same exact process we want to do before, right? We want to think about, is our graph in the middle? Is our graph at the top? Is our graph at the bottom? But importantly, we're not thinking about up and down anymore. We're only thinking about, I got it backwards. We're not thinking about left and right. We're only thinking about up and down. So I'll do the same kind of thing, right? Is our graph in the middle at 0? Yes. Is our graph up here at 3? Yes. Is our graph up here at 6? Yes. Is our graph up here at 8? Yes. Is our graph going to keep going forever up? Yes. Same thing. Is our graph down here at -2? Yes. -4? Yes. -6? Yes. -8? Yes. Is our graph going down forever? Yes. Our graph is going to be all the way from negative infinity to positive infinity. But the easier way to write that would be all real numbers. Okay. Now let's go to end behavior, okay? End behavior is an intimidating question to solve, but it is the easiest question to solve, okay? I always say that end behavior is so easy, a 5-year-old could do it, okay? I promise you, a 5-year-old could do it. Now, let's go up here. Let's talk about end behavior. End behavior is asking you, where is your graph at infinity and negative infinity? Okay. So imagine this. Imagine you zoom all the way out, okay, and you've got a giant graph, and you can see all the way over at negative infinity. You can see all the way over at positive infinity. The question is just, where is your graph? Okay, so let's imagine we're working with this graph, okay? And what's really nice is we can use Desmos for this, negative 3x plus 5. You can type it in. You can zoom out and 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 zoom out forever until you see 100,000 and a positive 100,000, negative 100,000. What this is saying, and just read it. It says as x, and then this arrow is basically as x goes to infinity. This f of x is basically a y. Y goes to blank. So again, as so easy a kindergartner could do it. Here's what we're saying. As your x's are going to infinity, so here's my x's. As my x is going this direction, as it's going towards infinity, where is the y going to, right? Basically, if I zoom all the way out, the end of the graph here is going to be down forever, right? I mean, this graph is just going down, 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 super far down, okay? And so because as I go towards positive infinity, my y's are going down, the answer is negative infinity. End behavior is a question that is literally asking you, are the ends of your graph going up or down? That's all it's asking you, okay? So now this second question says, as x is going towards negative infinity, what that means is, as my x's are getting smaller, as I'm going left, where is the graph going? Up or down? My graph is going up, right? This graph's going up forever. And so the answer over here would be positive infinity. And so basically you have two different end behaviors. Sometimes they'll be written like this, where it's a little bit more mathy, but sometimes it'll just be called, let me erase this stuff here. I don't know if this makes it easier, but a lot of students like this more. Sometimes it'll just be called, let's do red. This will be called right in behavior, and this will be called left in behavior, right? Because it's literally saying on the right side, I'm going down. On the left side, I'm going up. And lastly, let's talk about increasing intervals or decreasing intervals, okay? So this is a question where you're talking about, is your graph, let's see here. I guess I need to go back up here and define it. Increasing, decreasing. Is your graph going up or down? Again, another very basic kind of question. Is your graph going up or down? Okay, it doesn't take a rocket science to look at a graph and decide whether it's going up or it's going down. Now, what's really important with this is we need to talk about x's. Okay, so let me write this. Only write x's. Okay, that's super, super important. And we'll talk about why that is when we get to probably our second question here. So a really easy trick for this is to basically trace the graph with your finger. And I know I'm on the computer and it's kind of hard for me to show you doing that. But if I'm going to trace this graph, as I'm tracing the graph, am I going down or am I going up? Right? I'm going down. That's definitely not a super difficult concept. As I'm tracing it, I'm going down. So this whole time, I'm decreasing. Okay? As I'm tracing it, left to right, I'm decreasing it. So now what I need to do is write my increasing or decreasing intervals. And I need to only write it in terms of the x values. Now this is where this one gets a little tricky. Okay, this is where this one becomes one of the most missed questions out of all of these, because we're looking at basically the rise and fall of the graph. So we're kind of looking at the y values, but we need to write down only x values. So first of all, this graph never increases, right? We know for a fact it's going down, 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 it's going down. It's never going up. So no increasing intervals. Now decreasing intervals, when is it decreasing? From what to what? Okay, and this is where some people mess up, okay? And they say it's decreasing from a high number to a low number. But that's the y values. Okay, we're always going to write it in terms of our x's. So we would always put from negative infinity to positive infinity here. Okay, and again, this is always going to trip somebody up, and they'll always be saying, but I thought we were going from infinity to negative infinity. But again, remember, those are the y values, and we don't want y values. Okay, what we're saying is we're decreasing here, we're decreasing here, we're decreasing here, we're decreasing here, and that is from negative infinity to positive infinity on the x values. So remember that these are x values, not y values. Okay, now this was a really slow walkthrough through parent functions, domain and range, number of roots, in behaviors, increasing, decreasing. Let's pick up the speed a bit, and let's knock out a question like number 2. Now again, if you're not sure how this graph looks, you can type it in Desmos. But if you remember our car, we remember that this is an absolute value graph. Absolute value graphs are V-shaped. We know that this -1 here is going to move us right 1. And the reason it's moving us left and right is because it's an H. And the reason it's moving us to the right is because H is opposite. So even though that's a -1, it's going to move us right 1. And then we know that this -4 is going to move us down 4. Because that 4 is a K, it is on the outside of the shape, and it moves us in the same direction. So it's a -4, that means down. And so that means that our V shape should be right 1, down 4. 1, 2, 3, 4. So our V shape should be right here in this direction. We're going to draw a nice little V shape here. Okay, so now we've got our V shape. Now let's analyze this graph a little bit, right? First of all, what's the parent function? Okay, that one should be a piece of cake. You're going to take away all the numbers. All you get is a y equals x, and then whatever makes this a special kind of family, right? It's an absolute value graph, so we need to have the absolute values on there. Okay, so make sure you got your absolute values here, and it doesn't just say y equals x. Then you've got domain and range, number of roots, in behavior, increasing, decreasing. Okay. Last time we did these number of roots first, right? And we said number of roots is just talking about the x-intercepts. I've got one right here. I've got a second one right there. How many roots do I have? 2. Easy. Okay, now let's talk about domain and range. Where does my graph exist in terms of the x's? Okay, does my domain, does it exist over here? Yes. Here? Yes. In the middle? Yes. Over here? Yes. Over here? Yes. So, what is my domain? Easiest way to write it, all real numbers. Right, that fancy R shape. And that's because my graph is going left, my graph is going right. So we can put all real numbers. Okay, let's talk about range here. Is my graph going up? Is it going up forever? Yes, 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 yes. So my graph is going up forever. Is my graph going down forever? Yes, 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 no. Right? So we have an issue here. Okay? Our range is not all real numbers. Because it does not include all real numbers, right? The number -5 is not included in the range. The number -6 is not included. And so, we need to write something that is not all real numbers for our range. So, here's the way you do it. What is the lowest number that is included? Okay? Can we start at -7? No. Can we start at -6? No. Can we start at -5? No. Can we start at -4? Yes, of course, right? So we're going to start at -4. Actually, let me undo it and get rid of all those lines. We're going to start at -4. And then what is the highest number that we're going to go to? Obviously, we go to -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8. Are we ever going to stop going up? No. And so we need to be from -4 until infinity. Okay, we need a comma in the middle. We always need a parentheses on the infinity, but we need a bracket on the -4. And that is because we include -4, right? Our graph is at -4, and so we need the bracket there. Another way you could write this is y is greater than or equal to -4. Let me make sure that looks like it has an equal sign there. This is inequality notation. This is interval notation. So they're the same thing. But again, that's because every number equal to or bigger than -4, our graph exists. All right, in behavior. Remember, this is a question so easy a kindergartner could answer it. Are we going up or down on the ends of our graph? Okay, basically, if you were going to make the graph with your arms, would your arms be pointing up or would your arms be pointing down? So you can't see me now, but this is how the graph looks. Okay, on this side, is it going up or down? Up. On this side, is it going up or down? It's going up. Okay, both of our graphs are going up on both sides. Okay, well, that means it should be infinity, infinity. Because as x is going towards infinity, remember that's like the right end behavior. On the right side of our graph, y is going towards infinity. On the left side of our graph, y is going towards also infinity. Because they're both going up. And now the increasing and decreasing interval. Okay, so remember, when it comes to increasing, decreasing interval, you're going to want to trace your graph from left to right. Okay, so I'm tracing it. I'm going down, 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 down. Then I get to the vertex, and then I'm going up, 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 up. So I'm clearly not going decreasing forever. I'm not decreasing for all real numbers. Up here where we wrote this, we could have put all real numbers. That would have been fine. But I'm not increasing for all real numbers, and I'm not decreasing from all real numbers. Okay, my strategy for you here is start on the left side of your graph and go towards the right side of your graph. Okay, so when do we start decreasing? What do you think in class? What do you guys think? When do we start decreasing? We're going down, down, down. And in fact, we've been going down forever, right? We've been going down all the way since negative infinity. That's when we started going down. Now, again, somebody is always going to say, I thought we were up here at positive infinity, though. But that's the y value. We need to think about it in terms of x values, right? So here's the trickiest part. When do we stop decreasing? When are we going to stop decreasing? I know you guys know it's right here. That's when we stop decreasing. But what number are we going to use for that? This is a tricky one. Anybody know the answer? We're going to stop decreasing at 1. Which is not that crazy once you see the answer, but it's such a missed question in Algebra 2, right? We are, hopefully you would agree, decreasing all the way from negative infinity, decreasing, 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 stop. Well, I missed it a bit. Oh, I missed it again. Stop. Right? We're decreasing for this whole region here. Okay, and it is at 1 that we stop decreasing. Now, here's what happens. Literally half of the class will miss this question, and they'll put -4 here, right? Because they'll say, oh, look, we're decreasing until we get down to -4. But that is the y value. That is not what we want. We want x values only. So be very careful. It has to be 1. It cannot be -4. Then here's what makes decreasing, increasing pretty easy. Once you get the first one, the rest of them are really easy. Because once we stop decreasing, we're going to start increasing. So we can just use this same number twice, right? We're going to stop decreasing and start increasing at the same place. And then we're going to go until infinity because we're never going to stop increasing. Now, the last thing I want to say is we've used parentheses on the 1 here. Everybody knows it's going to be parentheses on infinity because it's always parentheses on infinity. But parentheses on the 1. We can't use brackets because if we use brackets, that would mean that we're decreasing, including 1, and increasing, including 1. You can't be decreasing and increasing at the same time, okay? You can't do both. And so this point right here is basically not included. We're decreasing on this side, right? We're going down, decreasing. We are increasing on this side. But right in the middle, we're not really doing anything. We're just kind of stuck in limbo. And so 1 does not get included. It needs to be parentheses. So increasing, decreasing will always be parentheses. You can never have brackets for increasing, decreasing. Okay, let's do one more. And I'm going to go super, super fast here, so keep up with me. Now, number 3, looking at this question, it's not in vertex form. It is not easy to graph from our head. We could do complete the square, but that would be a little tricky, and I don't want to do this question fast. So you could always just type this one in Desmos. You could see how the graph looked, and you could analyze it from there. So let's go down. Let's do number 4. Number 4 is, again, taking some notes on this. This is an absolute value graph. Absolute value graphs are V-shapes. We've got a plus 6 that is on the outside of the absolute value. This is a behind the car plus 6. So this is a up 6 k value. And I've also got a negative sign out front. And that negative sign out front is going to flip me upside down. So I should be able to graph this one just from my head. Normally the V shape would be in the middle, but I've gone up 6 and I've been flipped upside down. So let's see here. 1, 2, 3, 4, 5, 6. So now my V is up here. But I've also been flipped upside down. And so now my V is a downwards V. All right. I'm going to be going pretty fast here, okay? Parent function, y equals absolute value of x. Domain and range. My domain, all real numbers, right? Because I know my graph is going left. I know my graph is going right. I know my graph is in the middle. So my graph is everywhere, right? Yes, 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 forever. Okay, negative infinity to positive infinity. Now my range, yes, 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 no. Right? My range does not go up and down forever. My range has a top, right? This is the highest possible value of where my graph goes. So when I'm writing my range, I'm going to write what is the lowest number that is included. Well, 0, -1, -2, -3, -4, -5, -6, -7, -8. The lowest number that I'm going to include is negative infinity, right? My graph is all the way down at negative infinity. What is the highest number that I'm going to include? 1, 2, 3, 4, 5, 6, not 7. So 6 is the highest number that I'm going to include. 6. Now, do I need a parentheses or a bracket here? Does my graph include 6? Yes, right? 6 is a valid point of my graph. So I need brackets on there. And again, another way you could write this is that y is less than or equal to 6. Right? So now we need a less than graph because it's below 6. Okay? Number of roots is how many x-intercepts do I have? 2. End behavior. Again, it's pretty easy because it's both of them the same direction, right? On the right side, am I up or down? I'm down. On the left side, am I up or down? Down. Right? I'm down on both, so I put negative infinity for both. Now my increasing, decreasing interval. Okay? I'm going to trace it left to right. I'm going up, 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 stop going up. Then I'm going down, 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 down. So the middle point is right here. Okay? And we want to use the x value. So that's why I'm using a vertical line. Okay? As soon as you put a line that's a horizontal line like this, you're going to get the question wrong. Okay? We need to use the vertical line. And so which one of these are we doing first? Increasing or decreasing? We're starting with increasing. And basically, we're always going to start with a negative infinity. Right? Because we're always going to be starting over here. There's only one example of when we would not start with a negative infinity. But we'll not worry about that. Okay? So starting at negative infinity, we're going up, 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 stop. The last number that we're going up at is a 0. And again, there's always going to be somebody who's going to be confused, and they're going to say, I thought we were going up until 6. but that 6 is the y value, and we don't want the y value. We always need parentheses because we can't be going up and down at 0. But this is easy. Once we get the first one, the rest of them, we're just going to use this same number 0 again, right? Because we're going to stop increasing and start decreasing at the same place. We're going to include 0. Well, we're going to say 0, but we're not going to include it. We're going to have to put parentheses there, and there's our decreasing interval, right? And again, make sure you're comfortable with this. This needs to be a positive infinity. Somebody always is going to say, but we're going down. But we're down here at negative infinity. But that's not what we need. We're talking about x values. We are going down until positive infinity. Bless you. We're going down even all the way over here. We're still going down. Even all the way over here, we're still going down. So we need a positive infinity for that. All right, that is how you work with analyzing these graphs with these different metrics we're talking about today. Now, some things that you might have noticed, some things that you might want to keep in mind, okay? Our domain, all real numbers, all real numbers, all real numbers. Our domain was all real numbers for all 3 of the examples we did today. And if we look at our pictures here, okay, which pictures are going both directions forever? Okay, zoom in a bit, right? This first graph, domain, all real numbers, right? It's a line, it's going to have domain of all real numbers. The U shape is going left and right. Domain is all real numbers. The V shape, domain, all real numbers. The radical, the square root, for this graph, we would not have all real number domain, right? Because our graph has a stop right here. So it does not go left forever. And so domain is not all real numbers for the square root. It is all real numbers for the cube, and it is all real numbers for the cube root. So domain is really easy, literally 99% of the time, okay? Only the square root is different. All the other ones, you just put all real numbers and it's a piece of cake, okay? Now, some of these other ones, when it comes to the range, all real numbers. The range, all real numbers. The range, all real numbers. But the U and the V and the absolute and the square root, I don't know why I've said that 3 times now. The U, the V, and the square root do not have all real number range, right? Because they have bottoms and bottoms and bottoms. And it's also the same with in behavior, right? In behavior is going to be different, is going to be the same, is going to be the same. In behaviors are really strange for square roots, but in behaviors are going to be different, And so you'll start to realize that the parent functions solve a lot of these questions for you, right? As soon as you know it's a V shape, you know my domain's all real numbers, my in behaviors are going to be the same, my range is not going to be all real numbers, and you can already start to solve a lot of those questions. All right, that is how you look at analyzing these graphs. That is it for notes today.